Well, good morning. Everybody have a good holiday weekend. Get all caught up on your work and your sleep? No? Which? Both? Either? Well, before we get started this morning, does anyone have any questions over the last homework assignment?
Question number 53. Pi over 12, 15 degrees.
Well, let's see. Pi divided by 12 is 0.26. I'm sorry, say again? Okay, that's what I'm doing.
Look at the way it's in the book. I just want to make sure they made a mistake.
Yeah, they gave you the answer.
So I didn't misunderstand the question. They made a mistake.
That's a printer's error, yeah. And a free point for you. You had your hand up. Same question? Okay. Yeah, no, they were not sneaking in a new, unintroduced form of notation. It was just a printer's error. Yeah. What other? Any other questions from the last assignment? So then everybody's ready to get started on the unit circle? Because this is where all these functions are going to start to... Actually, the unit circle is pretty much how I manage to remember what I do remember about the various, there you go, trig functions. I'm going to diverge just a little bit from the book. If you've read the book, chapter 2, they introduced the unit circle with this. They simply set up a set of coordinates, place a circle of radius 1 unit centered on the origin, and then they set a second vertical axis tangential they call it the t-axis at x equals 1. And what they're trying to introduce through this exercise is they're trying to demonstrate to you that for every real number t, no matter what number you pick off of that vertical t-axis, if you consider it the point S, you can then wrap that axis like a string around the unit circle, and it will give you a unique point P of X and Y. Okay? You can do it in the positive direction to make a positive rotation around the unit circle. You can go down in the negative direction, make a negative rotation. And the point they make is that if you go more than 2 pi up the t-axis, then you'll just keep wrapping multiple times around the circle. But you will come back for every number t that you can imagine, you will get one unique point of P of X and Y on the unit circle, where X and Y are the XY coordinates of that point. This is how they're introducing the idea of the periodicity, of the fact that, the same point on the unit circle can be one angle, or it can be that angle plus 2 pi, it can be that angle minus 2 pi. There's an infinite number of angles that will bring you to that point on the unit circle. But for every angle For every length s on the t-axis, there is one and only one point on the unit circle at coordinates xy. So it is a function. Then they introduce these definitions for the trigonometric functions. Can everyone see from over here? Sine of t is equal to the y-coordinate at that point. Cosine t is equal to the x-coordinate at that point. Tangent of t is equal to the y-coordinate divided by the x-coordinate. Cosecant t is equal to, anyone want to take a guess? The reciprocal of the y-coordinate. Secant t is the reciprocal of the x-coordinate, and cotangent of t is equal to the x-coordinate divided by the y-coordinate, or the reciprocal of the tangent. As you should have already noticed from the first time we looked at the definitions of these trigonometric functions, cosecant is simply the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Here's my problem with the book and their approach. They just tell you this and say this is the way we define these numbers, and then you just believe that. But if you will think back, what were the original definitions that we used for the trigonometric functions? We were talking about, we define them with respect to a right triangle. Hypotenuse, opposite, and adjacent. And we defined the sine of theta as the opposite divided by the hypotenuse. We defined the cosine of theta as the adjacent divided by the hypotenuse. And we defined the tangent of theta as the opposite over the adjacent. Cosecant was the hypotenuse divided by the opposite. The secant of theta was the hypotenuse divided by the adjacent, and the cotangent of theta was the adjacent divided by the opposite. These were the very definitions that gave us the values of the sine of theta, the cosine of theta, etc. Now, using those same definitions, assume that the hypotenuse is equal to 1 unit. Now, everywhere on this coordinates on this circle is the coordinates of the unit circle. this circle now becomes the unit circle. That being the case, we know the cosine is equal to this length, and it is equal to the adjacent divided by the hypotenuse. Well, the adjacent is that x coordinate divided by 1. So the cosine of theta is equal to, on the unit circle, the x coordinate. The sine of theta on the unit circle is equal to the y coordinate. You work it out on every one of them, and we end up with these very definitions. And that frankly becomes the way I think of the sine and cosine function as the x and y coordinates of the unit circle. Now, if I have a larger radius, I can revert back to these definitions and find that if I want the y coordinate or the x coordinate of something out here at some radius r, then I know that the hypotenuse of that right triangle is simply r, and the y coordinate becomes r times the sine of the angle. Okay, now, does everyone see how these sine and cosine, how these 6 trigonometric functions relate to the xy coordinates on this unit circle? Okay. Now, once you know that, then their mapping of this extra t-axis to various lengths of s, or arc lengths, now you can get to there from here. So does anyone have any questions yet? Anything not quite clicking? Everyone's happy now thinking about sines and cosine functions as x coordinates on the unit circle for all these different angles.
That S point,
Uh-huh.
that's just simply that length laid down around the radius of the point, right?
That's all it is. In fact, in the book, I think they even tell you that as a mental exercise, you can imagine this S length being a string that you can then wrap around this circle. And however far it wraps, that's where you end up at your final coordinate points. Okay, well, then moving on, let's look at how we would find the values of the 6 trigonometric functions if all we have are the coordinates of a point on the xy circle. Let's say we go to the xy coordinates of -1/2 and the square root of 3/2. Seems like a weird number to pick, right? Well, it actually is a set of coordinates on the unit circle. How can we prove that these are, in fact, coordinates on the unit circle? Somebody? Anybody? Because that's the very first thing we've got to know if we're going to find the trigonometric functions for these coordinate points. Are they on the unit circle? Or are they just like really close to it? Say again? We can plot them, but if we just want to know, are they on the unit circle, how would we determine that? Just very quickly. Pythagorean's theorem. If 1/2 and the square root of 3 over 2 are the xy coordinates of a point on the unit circle, then it must be true that 1/2 squared plus the square root of 3 over 2 squared will equal, anybody? Say again? C squared, but in this case, C is equal to, which in the case of the unit circle is 1. So it's 1 squared, which is 1. Well, 1/2 squared is equal to 1/4. Square root of 3 over 2 squared is 3 over 4. 1/4 and 3/4 equals 4/4 equals 1. So we now know for a fact that 1/2 minus 1/2 and the square root of 3 over 2 are on the they're on the unit circle. So are the points 1/2 and the square root of 3 over 2, or 1/2 minus the square root of 3 over 2, and minus 1/2 minus the square root of 3 over 2. Once we know, because we're squaring, so the minus signs don't matter. Once we know that that point is on the unit circle, we know all 4 of those points are on the unit circle, and symmetry shows us pretty much where they're at. So now that we know the coordinates of a point that is, and we know that it's on the unit circle, how do we find the values of the 6 trigonometric functions? We're looking for sine theta, or, well, actually, we're just going to call it P, the point P. The cosine of that point, the tangent of that point, cosecant, secant, and cotangent. Somebody, anybody, off the top of your head, what's the sine of that point on the unit circle? Remember our definitions. The sine of this point is the square root of 3 over 2. Very good. Somebody want to holler out the cosine? Negative 1/2. The cosine of this point is not 1/2, it's negative 1/2. Just like the cosine of this point. What's the tangent? Which would be, you're right, it's the square root of 3 over 2 divided by negative 1/2, which is the square root of 3 over 2 times the reciprocal. You're dividing, multiplication is division by reciprocal. So the 2's cancel and you end up with negative square root of 3. Yeah. That's our tangent. Now the next three are just, look and write them down. What's the cosecant? So it would be 2 divided by the square root of 3. What's the secant? What's the reciprocal of negative 1/2? Negative 2. And the cotangent. And we could go back and do all the division again, but we know it's the reciprocal of the negative square root of 3, so it's negative 1 over the square root of 3. Point of information for all of you. You're going to notice, especially if you look in the back of the book at the answers, you're going to find that oftentimes they will write 1 over the square root of 3 as the square root of 3 over 3. Does everyone see how these are the same number? It's the same thing. That's equal to the square root of 3 over the square root of 3, which is 1, times 1 over the square root of 3. So if you run into that in your book, looking up answers, just recognize that it's just two different ways of, it's a more complex way of writing the same thing. Now, does everyone understand now how once we have a pair of coordinates on this unit circle, we already know we can immediately find that easily all 6 of the trigonometric functions? Are there any questions? Well, we're zipping right along this morning. Okay, there is one thing I want to point out here. It's a definition they present on page 117. And I guess it is worth pointing out. We started off with this string, this extra t-axis, and these lengths s. Well, they point out as an explicit definition in the book that if t is any real number, t is an expression of the number of radians in theta, then the sine of t is also the sine of theta. We already looked last week at how radians are in fact just real numbers. They're not units. So whatever that number is, if it represents a number of if it represents some rotation around the unit circle, whether it's a length or an angle of radians, okay, well then let me clear off some board space and ask a question. Who can tell me what a quadrantal angle is? Very good. Who said that out loud? Hoorah. Remember the XY coordinate axes, the Cartesian coordinates, are divided into 4 quadrants. Most angles will land in one of those 4 quadrants. And yes, that's a circle. You can laugh at me on your own time. Who remembers the four quadrants, how they're designated? Counterclockwise, in positive increasing angles. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. But if the terminal ray of an angle lands on one of the two axes, those are quadrantal angles. So let's find the exact trigonometric functions of the quadrantal angles. What's this quadrantal angle? Zero and 360. 360 what? Degrees. Or, in radians? 2 pi. Here, this quadrantal angle. 90 degrees. Pi over 2. This one? And finally, this one. Booyah. 3 pi over 2. Now, what are the coordinates of these 4 points? Here we have the coordinates of 1 and 0. Here we have coordinates of 0 and 1. Here we have coordinates of -1 and 0. And here we have coordinates of 0 and -1. Now we've got the coordinates of the points. Now coming up with the trigonometric functions. Just a matter of looking at the coordinates. Sine, cosine, tangent, cosecant, secant, and cotangent. At 0 or 2 pi. What's the sine? Nope. No, at 0 or at 2 pi. What is the sine? No, at 0, the coordinates are 1 and 0. So the sine of 0 is 0. What's the cosine? +1. What's the tangent? So 0 over 1, which is 0. Now we got to get careful. What's the cosecant? One over 0, but division by 0 is undefined. So the cosecant of 0 is undefined. I did show y'all the proof about 2 equals 1, right? Did I show y'all that proof that 2 is equal to 1? Let me shut this fool thing up. Everybody get ready to take notes. This is why division by 0 is undefined. You've heard it said that numbers never lie, right? Numbers don't lie, but people do. Assume that A is equal to B. For example, 1/2 is equal to 2/4. Okay? That means if we start off with A squared, that is equal to A times B. So far, so good? Oh, if we can do this, as long as we do it to both sides, we can do anything to the one side as long as we do it to the other. So A squared minus B squared is equal to AB minus B squared. How many remember your factoring in algebra? Right up there. What's the difference of perfect squares? The difference of two squares. A minus B becomes A plus B times A minus B. Very good? Here we can factor out a B. Becomes A minus B. Well, now we've got A minus B on both sides. It cancels. So we've got A plus B is equal to B. But A is equal to B, so that's actually B plus B is equal to B, or 2B equals B, therefore 2 is equal to 1, QED, quo erat demonstrata. It is proven. Hopefully every one of you can look at this and intuitively know that it ain't right. But who can spot the lie? Can anyone tell me where the lie is in this? Where is the error? Where? No. If A and B are equal, then A times A is equal to A times B. Say again? No. Nope. B plus B. A plus B. If A and B are equal, then A plus B is equal to B plus B. But if A plus B, if A and E and B are equal, what is A minus B? 0. So at this point right here, all we're saying is that something times 0 is equal to something else times 0, and that is universally true because 0 times anything is 0. So at that point, this and this are irrelevant. It doesn't matter what they are equal to. The issue then is, how did we cancel A minus B from both sides of the equation? When you're canceling a term, what you're doing is you're dividing by that term on both sides. You're saying I can divide this side by A minus B, which cancels it out, as long as I divide this side by A minus B, which cancels it out. But A minus B is equal to 0. And when you divide by 0, this is the kind of nonsense that falls out. At that point, anything is equal to anything. Okay? This is an important, this is a very important lesson to learn. Anytime you start canceling terms, anytime you start doing algebra, you make absolutely certain that you do not divide by 0 or everything becomes meaningless. So, for these quadrantal angles, when you have a sine is equal to 0, the cosecant is undefined. Of course, the secant is what? The reciprocal of 1, which is 1. And the cotangent is just the reciprocal of the tangent, which is No. Undefined. Because the tangent is 0, so 1 divided by 0 is undefined. What about at pi over 2? What's the sign? 1. Cosine? 0. Tangent now? Undefined. The cosecant? Cosecant is now 1. It's the reciprocal of 1, which is 1. The secant is the reciprocal of 0, which is undefined. And the reciprocal of the tangent, because the tangent is undefined, but the cotangent is 0 divided by 1. No, 0 divided by 1 is still 0. Remember, it's a shortcut to think of the cotangent as the reciprocal of the tangent. But when the tangent is undefined, you can go back to the definition of the cotangent, which is the x-coordinate divided by the y-coordinate, or the cosine divided by the sine. All right. Now let's look at pi degrees, or pi radians, not degrees. 180 degrees. Sine is 0, cosine is, booyah, very good, -1. Now the tangent, 0 divided by -1 is still 0. The cosecant, undefined. The secant, -1, and the cotangent, undefined. 3 pi over 2. Sine is -1. Cosine is 0. Well, now let me keep up. The tangent is -1 divided by 0, which is undefined. The cosecant is -1. The secant is undefined. And the cotangent is 0. You see there? You can actually get all 6 of the trigonometric functions faster than I can keep up writing. At those quadrantal angles, it's all ones, -1s, and 0s, and undefined. Do we have any questions? Yeah, and you'll find these table 2 in your book on page 118. Okay, let's look at something about not sure what word I want. Reciprocity, the cyclical nature of these functions. Let's look at integer multiples of these quadrantal angles. By an integer multiple, I mean, in the case of 0 or 2 pi radian. Well, you know what? Let's start at the pi over 2. That one will make more sense. What are the integer multiples of pi over 2? First one is 1 pi over 2, which is where we started. The next integer is 2 pi over 2, which is just pi. The next one is 3 pi over 2, which we've looked at. 4 pi over 2 is just 2 pi. Next one would be 5 pi over 2. Where's 5 pi over 2? $450. Where would that be? Basically, here we go. We just count them. We've got 1, 2, 3, 4, 5 pi over 2, and pi over 2 are the same points on the unit circle. They have the same coordinates on the unit circle. So pi over 2 would also be true for 5 pi over 2. 6 pi over 2 brings us right back to 180, or pi, which would be actually what? 3 pi. Six pi over 2, 6 divided by 2 is 3. So we've got 3 pi. What's the next one? 7 pi over 2, which is the same as 3 pi over 2. And 8 pi over 2, what's 8 divided by 2? 4 pi. Anyone want to hazard a quick guess as where 9 pi over 2 is going to be? Ten pi over 2 would be 5 pi. 11 pi over 2. 12 pi over 2 would be 12 divided by 2. 6 pi. Anybody noticing a pattern yet? Are you noticing that every one of these is the same when it increases by how many? 2 pi. So for any point on the unit circle, which forms an angle theta, is going to be the same as that angle plus 2 pi. And that's true for every angle. So if you start at 4 pi and you find the coordinates, then you can say 4 pi plus 2 pi is going to be the same coordinates and therefore the same 6 trigonometric functions. All right. Who's ready to delve into a little bit of algebra and geometry? This time, let's look for the exact values of the 6 trigonometric functions at angles of pi over 4. So we start with our unit circle. X and Y. Now if this is pi over 2, and pi over 4 is going to be exactly halfway between them. because pi over 4 plus pi over 4 equals pi over 2. So now we need the exact coordinates of this point, xy. What can we say we know first of all? We know theta is pi over 4. And we know that this distance is 1. And when I start asking you about the length of the radius, what am I generally trying to point you towards? Pythagorean's theorem. So we don't really know what x is or what y is, but we do know that x squared plus y squared has to equal what? 1 squared or 1. But we also notice, because this is along what does anyone notice about this ray, this line right here, along the hypotenuse? You'll notice that it is along the line where x is equal to y. So out here, x equals 1, y equals 1. Everywhere along that line, x and y are equal. Because it's bisecting the angle. It's at 45 degrees. Okay? That means we can rewrite this as x squared plus x squared is equal to 1. Or 2x squared is equal to 1. That gives us x squared is equal to 1/2, and x then is equal to 1 divided by the square root of 2. Although the book will probably write it as the square root of 2 over 2 for reasons I explained a while ago. Well, if that's our x coordinate, and x is equal to y, we know that that's also our y coordinate. So we know for the angle pi over 4, we know the p of xy, the point xy is at the coordinates of 1 over the square root of 2, 1 over the square root of 2. And we know that that point is on the unit circle. So, what does that mean? What does that tell us? What's the sign of pi over 4? What's the y coordinate? 1 over the square root of 2. What's the cosine? 1 over the square root of 2. And it should be fairly intuitive to you that because of the particular symmetry of the geometry here, you would expect it to be the same on both sides. What's tangent? No. 1. It's 1 over the square root of 2 divided by 1 over the square root of 2. Anything divided by itself is 1. Cosecant. It's the square root of 2 over 1, or just the square root of 2. The secant, Same thing, square root of 2, exactly. And the cotangent. Again, we got 1. What would be the, let's use a little symmetry. What would be, that's 2 pi over 4. So we start here, we go to pi over 4, 2 pi over 4. What would be the six trigonometric functions at 3 pi over 4? Which brings us 1, 2, 3 right here. What's the sign? What would be the y coordinate here? The y coordinate is the same, it's still 1 over the square root of 2. What's the x coordinate? Negative 1 over the square root of 2. So what's the sine function? One over the square root of 2. Cosine? Negative 1 over the square root of 2. Tangent? Negative 1. The big brain on the little lady in the front row. Hoorah. You'd be surprised how many people, that negative sign, I don't mean to embarrass you, please don't forgive me, but the fact is that negative sign will sneak up and bite you. Pay attention to them. What's the cosecant? Square root of 2. Secant? Negative square root of 2. And the cotangent? Negative 1. We keep counting around, there's 3 pi, here's 4 pi over 4, or just pi. 5 pi over 4. What do we have for coordinates now? There it is. Sine? Cosine? Okay, now everybody be careful, pay attention. Now what's the tangent? Plus 1. Because it's a negative divided by a negative. Cosecant? Negative square root of 2. The secant? Negative square root of 2. And what's the reciprocal of plus 1? Still plus 1. That's 5 pi over 4, 6 pi over 4. Well, 6 divided by 4 is equal to 3 over 2, so that's just 3 pi over 2 again. Seven pi over 4. Now what are our coordinates? X, positive 1 over the square root of 2, and the y coordinate is minus 1 over the square root of 2. Okay. Our sine, negative 1 over the square root of 2. Cosine, 1 over the square root of 2. Tangent, negative 1. Cosecant, negative square root of 2. The secant, and the cotangent, negative 1. Everybody see how we got all of that? And these are exact values. We didn't round off any decimal places anywhere. I'm looking at this example they work here for you, and they tell you to find the exact values of some of these. I want to make sure everybody sees what's going on here. In the first example, they say do this without using a calculator. Just what is the product of the sine of 45 degrees times, what's the next one? The cosine of 180. (180 degrees). Just without using a calculator, without rounding, what's the sine of 45 degrees? (45 degrees is pi over 4. 45 is half of 90. So half of pi over 2 is pi over 4. The sine of pi over 4, the sine of 45 degrees. Anybody? One over the square root of 2. What's the cosine of 180 degrees? Which is pi. The cosine right there. -1. So the product of this, the product of sine 45 times cosine 180 is -1 over the square root of 2. Exact value, no calculator needed. Does everyone remember how to convert between degrees and radians? And from radians back to degrees? From last week. Okay, that's fair. That's fair and that's fine. But here again, we can see it just visually. We know that for pi radians, you have 180 degrees. So pi radians is equal to 180 degrees. Therefore, pi radians divided by 180 degrees is equal to 1. And you can multiply pi radians, anything by pi radians per 180 degrees, and if you or you can multiply anything by 180 degrees divided by pi radians. In this case, 45 degrees times pi radians per 180 degrees, or the degrees cancel. Plug that into your calculator. Now, obviously in the case of 45 degrees, we already know that that's pi over 4, but if you plug that into your calculator, you get 45 divided by 180 is 0.25. You multiply that times pi, and that gives you some decimal numbers, 0.785 and some more. That many radians. But if you multiply that times 4, you'll find that it gives you 3.14159 ... the value of pi. So if you do the conversion, you get the decimal notation of pi over 4. It's important to remember this. We talk about, we write these numbers as fractions like pi over 4 or 3 pi over 4. Well, pi is a real number. So these are all actual numbers that you can punch into your calculator, round it off to so many decimal places. And it's important that you don't forget that. These aren't, the square root of 2. It's not a nice short decimal notation number, but it is a real number. And this is the exact value, whereas 0.707 is an approximation. It's close enough. Okay. Got some more time, so let's do, those are pi over 4. I'll clear the board up some and we'll start again. You may recall last I don't remember if it was last time or time before, but I pointed out that there was a table in the book where they had lots of nice exact fractions of pi. This is where they come from. This time we're going to look at the exact functions of pi over 6 and pi over 3. Now, how many degrees is pi over 6? Somebody take your calculator, punch in pi, and divide it by 3. Okay, pi over 6. It gives you something like 0.523 and some more numbers. That's radians. How do you convert from radians to degrees? You multiply by 180. And then divide by pi. And what does it give you? It should give you exactly 30. Pi over 6 is 30 degrees. If you do the same thing for pi over 3, you're going to get twice that. Pi over 6 times 2 would be pi over, or am I doing that backwards? Pi over, yeah. Yeah. Point is, you do this, you end up with 60 degrees. So here is pi over 6. Here is pi over 3. Or 30 degrees and 60 degrees. Well, let's start with this one. We go up 60 degrees, a distance of 1 to the unit circle. And we get a right angle, a right triangle. Some distance A and some height B. Okay? Well, if we flip this angle over, here we know that this is 60, this is 30. Why do we, and those are, we know that because they have to add together to equal 90 because all three have to add up to 180. Okay, well that means this is also 30. This is also 60. But that means that this 30 plus 30 is equal to 60 as well. And that means we now have an equilateral triangle where all three sides are the same. That's one, and obviously that's 1 because we started off with a radius of 1. So right off the bat, we see the x-coordinate A. We know that 2 times A is equal to 1, and therefore A is equal to 1/2. And that gives us our first coordinate on this right here. One half. Now we need this coordinate, B. How do we find B? Pythagorean's theorem, thank you. You people are going to learn to love Pythagoras by the end of this class. Pythagorean's theorem, we know that a squared plus b squared equals 1. And a squared is 1/2, so a squared is 1/4 plus b squared equals 1. That means that 1 minus 1/4, or 3/4, is equal to b squared, and therefore b is equal to the square root of 3 over the square root of 4, which is 2. Does everyone see how I got that? So we now have the point 1/2 and the square root of 3 over 2. Now, without going through the entire exercise again, I'm going to ask, do you see how we could do the same exercise, but by symmetry? You can see that if we did go through that exercise again for this triangle, flopped it over, we would end up with these point coordinates being the square root of 3 over 2 and 1/2. Does everyone see that? Or do we need to go through the exercise and actually derive that? Well, then we have the coordinates for the points on the unit circle at pi over 3 and pi over 6. So start with pi over 6. What's the sign? 1/2. What's the cosine? Square root of 3 over 2. And the tangent? One half divided by the square root of 3 over 2 would be 1/2 times 2 over the square root of 3. 2's cancel, and we end up with 1 over the square root of 3. Cosecant, secant, and cotangent. Just the square root of 3. Repeat it for pi over 3. Now what's the sign? And the cosine? 1/2. Tangent? Square root of 3. The cosecant? 2 over the square root of 3. The secant? And the cotangent? 1 over the square root of 3. Again, we can go through multiples of these angles. Adding 2 pi. Well, actually, if we go to, before we do that, we could come over here. What's this one? 2 pi over 6. 2 pi over 3. 2 pi over 6. Anyway. Yeah, this would be 4 pi over 6. This is pi over 6. 2 pi over 6, which is pi over 3. 3 pi over 6. Yeah. I am trying to rush past doing the multiples of these angles. I think you can see how using the same kind of symmetry that it doesn't matter what point you are on the circle. Any point on the circle in this quadrant, if we're talking quadrant 1, every point xy in quadrant 1 is going to have a plus x and a plus y. Okay? In quadrant 2, it's going to be minus x and plus y. In quadrant 3, it's going to be minus x and minus y. And in quadrant 4, it's going to be plus x and minus y. So the functions are going to be the cosine and sine, the trigonometric functions. The rotational symmetry is always there, but you can identify which quadrant you're in and which specific point you're at by the signs of the functions, by the signs of the coordinates. Does everyone see how that works? We only got a few more minutes, and I know this is part of the homework assignment, so I really do want to get to and cover this. Do some more cleanup here. What if you were given just 1 point on the unit circle? Okay? Let's draw our unit circle. And let's say you're given a single point, that the x-coordinate of 1/2. Where would that put you on the unit circle? Exactly. You know that the x-coordinate is 1/2, but that could either be here or here. So by having only one coordinate, you're only narrowing it down to one of 2 quadrants. But if someone told you that you were on the unit circle at an x-coordinate of 1/2 and you were in quadrant 4, you now know exactly which point you're at. And from that information, you could then find all 6 of the trigonometric functions. You know that cosine is equal to 1/2. You may not know the number yet, although we probably do, but you know that the sign is going to be negative because you're in quadrant 4. And you know that it's going to be 1 is equal to the sine squared plus 1/2 squared. Sine squared plus 1/4 is equal to 1. Sine squared then becomes so it's the square root of 3 over 2. And you've got your sine function. And then you can, once you have sine and cosine, you now know that you have the tangent. Once you have those 3 functions, the other 3 are just the reciprocals. Just make sure that you, especially on those quadrantal angles, make sure that you don't run across anything that's undefined. No division by 0. Now, one more thing to prep you for the homework assignment. What if you were given an x coordinate or a y coordinate? That was outside the unit circle or inside the unit circle, but some coordinate that's not on the unit circle. Say you're given an x coordinate of 2. That seems like that's a fairly safe number to start with. Well, if the x coordinate is plus 2, you know immediately that you are either in quadrant 1 or quadrant 4. And so your sign is either going to be positive or negative depending on which quadrant you're in. You also know that you're going to have a radius greater than 1, and it's going to be equal to 2 squared plus y squared. Do you have enough information yet to find all of the trigonometric functions? Not really. Because every one of these points on this vertical line, you can plug in and find a solution. Find an r from 2 to a little over 2. Okay? Now, what if somebody gives you this coordinate? Two and 1.5. Now you have the coordinates of a point. All you need is this radius. And you can find that radius by Pythagorean's theorem. Come back, and I've already erased them. But once you have that information, you have the radius, and you have the coordinates of the point. How can you find the coordinate? How can you find the 6 trigonometric functions? You know that R, going back to those original definitions, of the sine being the opposite divided by the hypotenuse, the cosine's the adjacent divided by the hypotenuse. From those definitions, you can write that r times the sine of theta is equal to this y coordinate. You can write r times the cosine of theta is equal to this x coordinate. You can write that the tangent, that r times the tangent of theta is equal to the opposite divided by the hypotenuse. Does everyone see how that, with that information, with the coordinates of any point, you can determine your radius, and going back to the original definitions of the sines of the trigonometric functions, you can then solve for all 6 of the trigonometric functions. Any questions? Okay, then I guess I will see you on Thursday.